Yeah, so I'm Max Bloor. I'm a first year PhD student at Imperial College London. I'm supervised by both Antonio Del Rio Shanona and Calvin Sai, and I kind of bridge the gap between like the computation optimization group and also the optimization and machine learning group in chemical engineering. So today I'll be talking about control-informed reinforcement learning and our package PC-GYM, which aims to connect reinforcement learning and chemical process control, essentially. So you may have heard of reinforcement learning through the Netflix documentary where they beat the best player at Go. And since this documentary, there's been lots of research interest in reinforcement learning due to this success in other fields. So we've seen it spring up, especially in the control communities and then into the process control communities. So we can kind of transplant the same ideas that have been used, say, in this Netflix documentary, into chemical process control. So to start off, I think you might not be too familiar with reinforcement learning, but we're essentially trying to learn a control policy. So some mapping between a state, which could be your concentration or temperature, and then some control action, so like the cooling temperature around your reactor. And the main advantages we see for chemical process control is the fact that it's model-free. So you're using a neural network to define your control policy rather than having a model of your reactor and then using that to determine your control action. And then it also has this fast online inference stage. So you're kind of moving that optimization to the offline setting. So online, you're able to make decisions very quickly. However, to train these algorithms, of course, the main drawback usually is the fact that they're sample inefficient. So that means that we're going to use lots of different states, actions, and reward pairs to determine our optimal control policy. So I think we should just go through what is reinforcement learning. So in the framework, we have an RL agent. So this is something that takes in the state and gives us an action. So it's usually represented as a neural network in deep RL. And then we have some environment, which could be your chemical reactor, a whole chemical plant, your experiment. But it's essentially something that's going to take you from this time step now to the next time step, according to some like nonlinear dynamics. So I've talked about states and actions, but what are they? So a state is defined as what is enough information to make a decision with. So it's usually up to the person to define that as from the environment. And then your action will be the control action on the environment. So it'll be your cooling temperature, for example, or it could have been the light, like we saw in a previous presentation. And then this environment will say it will simulate us to our next time step, and this kind of closes that loop. However, we have no goal for our RL agent to optimize towards. So this is where a reward function comes in. So this defines essentially the goal of our RL agent. So this agent will be optimized towards maximizing this cumulative reward over some defined time span. So this reward could be defined as the kind of economics of your plant, or minimizing some emissions, or it could be tracking some set point, so minimizing that error. So this, if you've read any RL papers, is usually modeled as a Markov decision process. So this is a mathematical formulation modeling what we've just talked about. And the main assumption behind this is the decision that we've made in this time step now isn't necessarily dependent on the past states and actions. And again, we can formalize our reward or our goal function. And this is that we're trying to find this optimal control policy pi star, and this will maximize our cumulative reward. So I'm going to talk about the first kind of part of my work. So this is our package PC-GYM. So let's move it along one slide. But this PC-GYM is going to make up our environment section. So this environment, as I said, is essentially like a simulator taking us from one time step to the next time step. And these exist widely for fields such as robotics, these classic control problems like you might have seen cartpole. They also exist for Atari games. And they've also been slightly branching out into other kind of communities like operational research. However, for our field of chemical process control, there isn't such a library. So this is the kind of gap that we hope to fill with PCGym. But you may ask yourself that this is kind of reinventing the wheel slightly, but in chemical process control, to really map or really to simulate the real problems, where we need to input disturbances and constraints which aren't necessarily present in these kind of robotics or classic control examples. And this helps us really kind of simulate our real chemical process control problem. So I guess we'll go for a slight example. So what can PCGym do? So of course you can import the library in Python, for example, and then we can define an environment object. And this is defined by a dictionary of parameters, and these parameters basically include the dynamics of your function. So we've got pre-made dynamical models of CSTRs, liquid-liquid extraction columns, distillation columns, heat exchangers, for example, all classic chemical engineering units, essentially. And then furthermore, like I just mentioned, you can also input or define your constraints on your problem, so that your RL agent may be penalized for going above a certain temperature, for example. And there may also be like disturbances to your system. So maybe halfway through your simulation, your feed concentration will change. And this is trying to replicate what may happen in real life. So you might get different feed concentrations from different suppliers, and your control algorithms should be developed in such a way that it can handle these. So I'll move on. After you've defined your environment, so the PCGym uses the kind of OpenAI's GYM framework, which allows it to interact nicely with off-the-shelf RL algorithms. So for example, if you've worked with RL before, you'll know stable baselines, but this is essentially a library of RL algorithms pre-implemented for you. So you can define this policy and then train it for 30,000 time steps. And then within PCGym, we can roll out this policy and then plot it. And inside of PCGym, we've also included what we call an oracle. So this is essentially a model-based controller that is using the perfect model to optimize the control trajectory. So this is is another thing that maybe not included in other GYM libraries, is the fact that you can now have a look at how far away you are from the optimum. So this gives you a sense of the optimality gap to the kind of model-based controller compared to your data-driven RL algorithm. So that kind of wraps up the kind of PCGym side of things. So I've introduced reinforcement learning as this model-free control framework, and also PCGym as a way of modeling our environment and giving us like a user-friendly version, user-friendly, accessible version of chemical engineering units. And then I'll talk about my kind of second project on my my PhD, which is looking at the RL agent side of things. So you may have heard of PID controllers. I usually give this talk at more control-focused conferences, but essentially what you need to know about a PID controller is they're used throughout industry. They're used due to their simplicity and reliability, and they're focused on these three parameters: a proportional, or KP, KI, and a KD parameter. And they also utilize this error term. So this error is the difference between the kind of set point, so the temperature, per se, that you want to be at, and the temperature you are at now. And as you can see, they're like a linear combination of variables, so they in turn are quite good at linear systems. So why am I introducing these? So by the end of this section, I'll be leveraging this kind of inherent control structure that we have and the stabilizing properties we have in PID controllers to kind of augment our reinforcement learning algorithm. So like I just said, let's kind of ask the question why we could, or what would be the difference between PID and RL. So PID, as just presented, is this kind of rule-based equation control structure, whereas RL, you need to learn your control policy using a deep neural network. And of course, the PID is quite simple due to its three parameters, whereas RL, obviously with a neural network, will have quite a lot of parameters. The PID as well, because it has this error term, it has this stabilizing property of it. They will always try to track the the set point essentially. However, in reinforcement learning, it depends on the training data. If you've included data on disturbances, then maybe it will be robust to those disturbances. And again, for nonlinear systems, due to the neural network in RL, we can handle them quite effectively. And the same goes for varying dynamics. Due to the fact that you can do online training in reinforcement learning, you have that ability to adapt to varying dynamics throughout your, over some time span. So just to touch on some other works that have combined reinforcement learning and PIDs, they've usually assumed this a static controller. So you know those three parameters I just talked about. So they're not going to change over the time span. You're just going to set them and essentially optimize your parameters of that PID controller. So you're not changing them over some time span. And we basically believe that this doesn't necessarily utilize the potential of RL agents. So this is where I present control-informed RL. So we have our neural network on the left, or here on the right, which is a standard neural network, which takes some observation of our reactor, and then it outputs these three parameters at each time step. Then we pass this to our PID controller, which is our control structure essentially, and then this gives us our control variable. So if we dive into our neural network, so it's parameterized with theta, and it provides us with this nonlinear function approximation. And like I said, it takes observation and outputs our PID parameters at each time step. And our PID controller is parameterized by this output of the neural network, and it provides this control structure. And then it takes the inputs of the current and the history of set point errors and outputs our control input to our system. So we need to find these the parameters of our deep neural network. I think we should just preface this if you've done any RL before. This is just one option for optimizing your deep neural network. So we've used particle swarm optimization here. Essentially, we're trying to find the best theta to maximize this cumulative reward function, reward. So there are some advantages to using particle swarm. So it can explore the policy space quite effectively. You can also evaluate different policies in parallel, and it's relatively simple to implement compared to, say, policy gradient algorithms. So in summary, we've got this neural network and then a PID controller, which implements control structure into our RL agent. And then our parameters are found with PSO. And now we'll test this methodology on a chemical process control example. So here we have a kind of general CSTR where we've got two reactions, and we're trying to control the concentration of our middle species, essentially. And we can observe the concentration, temperature, and volume of a reactor at the time step now and one time step before. And we also can observe the current set point for both the controlled variables. Our two control inputs are the flow rate into our reactor and the jacket temperature of our reactor. And then this reward function, which defines the kind of goal of our RL agent, is essentially a weighting of the error to our set point. And then we also have this penalty term, gamma delta U, which essentially penalizes large changes in control inputs. So this helps stabilize the input to the system. And then we test on both a set point tracking and disturbance rejection scenarios. And then we also, so we're talking about what we actually train our RL agent on. So here we have the operating space of our reactor. So in the blue line is essentially if you change the cooling temperature, what steady state concentration of B do you get to? And these three colors of circles I have on the blue line are three kind of sub-episodes. So we're kind of training on set points at the lower end of our operating space, the middle, and then at the top. So you can kind of see these kind of spread out evenly across the operating space. And then to test the agent, we kind of interpolate between these training data samples with the two kind of top orange triangles. And then you can see in our bottom orange triangle, we go slightly outside our training regime to kind of test the kind of generalization of our RL agent. And of course, we compare to kind of the two components of our method, our pure RL implementation, which is the exact same as our control-informed one, but with that PID layer removed. And then obviously we then compare as well with just the static PID controller, so the last layer of our methodology. So these are the learning curves. As you can see, compared to the pure RL implementation, the control structure that's been implemented on our control-informed reinforcement learning massively helps in the learning. It also initializes a lot higher due to it already having this control structure embedded in it. And then if we go to our set point tracking example, I think the first point to look at is this generalization set point, which is our lower set point on the left here. So that is showing that our pure RL implementation, because it doesn't have this structure, control structure implemented before it, is finding it very hard to generalize to that lower set point. And then the other two set points, it's able to track it fairly well, but not necessarily as well as the two methodologies with a PID controller. And then if we look at our orange line, which is our PID controller, we can see because we've got the static gains, and these gains will be great for one part of our operating space. It can do really well on the lower set point, but as we go across our operating space, we can see it overshooting on both the set points. And then our method, which is a blue line, tracks all the set points fairly well. It overshoots slightly on the middle set point, but it's also able to generalize unlike the pure RL implementation. And if we have a look at a disturbance rejection scenario, so this is when we have a step change to our feed concentration of our concentration of A. We can see that we train across 3 different disturbances, and we train, in this case, we train both the control-informed and pure RL implementations. And then we test on essentially an interpolation between these 3 disturbances. And you can see here, and I think it's a good point to mention that all these disturbances aren't observable to the RL that we've implemented. So the RL that we're talking about here will have no knowledge of what the underlying model is doing, essentially. So we can see here that due to the PID controller having this error term, it's able to stabilize the system back to the set point when that disturbance occurs around 15 minutes. However, due to the reinforcement learning, the pure RL implementation having no knowledge of this change, essentially, because it can't observe the disturbance, it settles for this compromise policy where it's below the set point before the disturbance and then it's above the set point afterwards. So today I've introduced 2 kind of works of my PhD, which are PCGIM, which provides a platform for developing RL algorithms for process control, and then control-informed reinforcement learning, where we're integrating this PID control structure into our deep reinforcement learning agent. So we can see that the control-informed reinforcement learning improves the sample efficiency and also the generalization. However, you do lose a bit of flexibility due to you imposing this control structure onto your RL agent. So yeah, wrap me up. So, yeah.